Today I'll talk about derivation of continuity equation for pipe flow. Continuity equation for pipe flow is rho 1 A1 V1 is equal to rho 2 A2 V2. Now derivation of continuity equation for pipe flow. The general mass balance equation for control volume with rate of mass generation or consumption states that rate of mass in minus rate of mass out is equal to rate of accumulation. Now coming to the assumptions for pipe flow. For steady state flow in a pipe, so rate of mass generation and consumption is 0 because there is no chemical reaction happening inside the pipe flow. Then rate of accumulation is 0 because steady state implies no change in mass over time. So mass balance simplifies to rate of mass in minus rate of mass out, means mass flow in is equal to mass flow out. Now here is a one pipeline. So if you consider the point is 1 and this is point 2, in point 1 velocity is V1 and diameter is D1, and point 2 velocity is V2 and diameter is D2, and also consider at point 1 that density is rho 1 and point 2 the density is rho 2. Now from that mass balance, so inflow mass is nothing but rho 1 A1 V1 and outflow mass flow is nothing but rho 2 A2 V2. So according to the continuity equation, so that we got from earlier slide, that mass flow in is equal to mass flow out. So here we can write mass flow in is equal to mass flow out. So mass flow in is rho 1 A1 V1 is equal to rho 2 A2 V2. So this equation states that mass flow rate must be conserved in the flow. Now if we consider that fluid is a incompressible fluid, so density remain constant. So here rho 1 is equal to rho 2, then we can write the continuity equation as A1 V1 is equal to A2 V2. Now we know A is a cross sectional area, that is pi by 4 d1 or d square. Now for A1, so that will be pi by 4 d1 square, and A2 will be pi by 4 d2 square. So now if I plug d1 and d2, so we'll get that d1 square v1 is equal to d2 square v2. So here d1 and d2 are the diameter of the pipe at point 1 and point 2. So this simplification indicates that product of cross sectional area and fluid flow at any 2 points along with the pipe must be equal. Here so d1 square of diameter and into velocity, that at any 2 points along with the pipe must be equal. So now we got d1 square v1 is equal to d2 square v2. So now if I write d1 by v2, so that will be d2 square by d1. So now here I am going to talk about effect of diameter change on velocity. If diameter will change, how velocity will affect. Now diameter increase, suppose d1 greater than d2, what will happen? So point 1 diameter is larger than point 2. So obviously from this V1 less than V2 means that as diameter D1 is larger, so velocity will be smaller, and D2 is smaller, so velocity will be larger. So this is because the flow rate A into V must remain constant, and a smaller cross section necessitates a higher velocity. So if we change with 2 points, so we can also tell, or another way, from flow rate we can also tell that smaller cross section necessitates a higher velocity. So if diameter increases, d1 less than d2, conversely if the diameter of the pipe increases, the velocity of the fluid must decrease. A larger cross section area allows the fluid flow more slow while still conserving the same flow rate. So that's it for that continuity equation. Thank you.